Hi, it's time for another math easy solution. Trying to discuss another applied project, basically in my calculus book at the end of each chapter as an applied project. It's a pretty useful application for calculus, so I'm going to go over this example, which is basically building a better roller coaster, and go over this word problem right here. Basically, it says, suppose you are asked to design the first ascent and drop for a new roller coaster, and by studying photographs of your favorite coasters, you decide to make the slope of the ascent or the rise 0.8 and the slope of the drop negative 1.6 here, so it's going down at that slope. And basically you decide to connect these two straight stretches, y equals L1 of x and y equals L2 of x, with part of a parabola, y equals f of x equals a to the power of x squared plus bx plus c, where basically x and fx are measured in feet, so that's what units we'll be working with. So, but for the track to be uniform or smooth, there can't be abrupt changes in direction, so you want the linear segments L1, L2 to be tangent to the parabola at the transition points P and Q. It basically means that the derivative has to be the same at these points. See this figure below, and to simplify the equation, you decide to place the origin at P. So if we were to draw an x and y curve, it would be like this. This would be x and this would be y, and basically 0, 0 would be at this P. As you can see, this is the part of the roller coaster you're supposed to design, and there's straight lines at that are tangent to this point, and there's this another straight line right here tangent to here, and this dashed line is this parabola f of x right here. It goes like that. So let's go with the first question. States basically, suppose the horizontal distance between P and Q is 100 feet. That's basically this distance right here is 100 feet right here. And basically write equations in A, B, and C that will ensure the track is smooth at the transition points. And then part B and then A are the same thing. I'll do these all in one. Basically, part B is saying solve for A, B, and C to find formula for f of x, but this is the same thing. So I'll just do A and B right now. I'll go over the example on part 2 in a bit. Yeah, so if you're to basically go over example on part A and B of question 1, if this is f of x equals ax plus ax squared plus bx plus c, so this is the function f right here, and if we were to draw the origin at P, this number, this point is 0 and 0, and we know at the end of this segment we have, at this point is basically 100, and then we don't know what this is, what's called y, etc. And if we just draw a dashed line to continue the parabola, then at this point we have a line like this, and this is going to be our L1, and then a line like this is going to be our L2 right here. So now we need to find these A, B, and C right here, and we could do that basically by making a set of equations. We know that, we'll just write that derivative down first. So derivative of f prime of x equals to 2ax plus b. That's this derivative using power rule. So this is the derivative of that, and we know that at the origin at P we have f of 0 equals to 0. That's just the origin. So plug this in. So we just plug this into f of x right here. We get 0 plus 0 plus 0 equals c. So c equals to 0. So we found out what 0 is. And now we know that the derivative at 0 right here, this has to be what we wanted to design the ascent. And this has to be 0.8 right here. Yeah, and it has to be 0.8 because we've already defined the slope here as 0.8, and then this slope right here as negative 1.6 based on our design that we've chosen initially. So now this equals to, just plug in 0 in here, we'll get b right here because 2a times 0 is 0. So we have equations for c. We have equations for b. Now we could solve the last one. And now the last conditions we have is that at this point we know the derivative at 100. So we know that f prime of 100, we're defining that as negative 1.6. So if we just plug this in, so we get this 100. So 2a 100 plus this 0.8 is b. So we go plus 0.8. Equals to negative 1.6. So we can solve this around, subtract 0.8 from 1.6, so we get negative 2.4 equals to, well, 2a times 100. I'll divide out the 2, so we get, and then divide by 100, we get basically a is equal to negative 2 divided by negative 2.4 divided by 2 is negative 1.2 divided by 100. So we're getting this 100 out of there, and this equals to what is this 1.0? We go 1 2 decimal place, so 1 2. So this is what a is. So we have our a, b, and c, and then our f of x is gonna equal to, yeah, so we just plug in those a, b, and c. C is 0. Remember, we get this equation for f of x right here, so this parabola. So that's our answer. And now basically let's look at question C. Plot L1, F, and L2 to verify graphically that the transitions are smooth. So to do that, we need to first find functions for L1 and L2. So we look at L1. Remember, they're equations of a line, so we go L1 is equal to mx plus b, just a basic equation of a line, and we know m is going to be 0.8, so x plus b. Now this b is different from the other one, I'll just leave it at b just to make it easier. So we have x plus b, so we know that at the origin, at basically at x equals 0, L1 has to equal 0 because that's the origin right there. So we get L1 of 0 equals 0 equals, well, b we plug in there, so b is 0, so we have L1 of x equals 2.8 of x. And then now for L2, this also equals mx plus b. Remember, these are just different m and b's, just leave it the same one. So now this equals to, we know negative 1.6 is m, x now plus a new b, and now we know that basically L2 of 100, this has to be equal to the same as f of 100, and we can just plug that in first to get f of 100. This equals to negative 0.012 times 100 squared plus 0.8 times 100, and plug this in the calculator. We get, yeah, so in the calculator we'll just get negative 40 right here. So then we know that this point is negative 40, so we could plug that in. So we'll have basically, let's go negative 40 is equal to negative 1.6 times it by 100 plus b right here. And now solving for this one, this would just be negative 40 added to 160, that's 1.6 times 100. So we get negative 120. Actually, I mean positive 120, because we're adding to this one here. Will be basically negative 40 plus 160, that's 120 equals to b. So we have our function L2 of x equals to negative 1.6 x plus 120 right here. So that's our equation. And now if we graph those three equations, we have this one right here. This is L1. This is our f, and as you can see, this is our L2, and we basically graphically it looks really smooth here. So it basically, this line goes smooth, and then all of a sudden it goes back to this parabola, and now we have a straight segment right over there. So it's smooth right here, and this we just verified it, so that answers our question. And now part D right here, find a difference in elevation between P and Q. If you look, P and Q is just from here to here. And that difference, well, that's just going to be the difference of the y values. So we know that, so basically they're asking the elevation difference, or what is this point right here, and that is, well, 0 minus, well, we already know that this is going to be 40. So this is a 40, I mean negative 40, so our difference is going to be negative 40. So we could just go, let's write that down right here, part C. We'll go f of 0, and then basically, yeah, f of 0 minus f of 100. This would just equal to 0 minus negative 40, so this equals to 40 feet difference. Remember, this difference, that's why I have it positive, because they just asked what the difference is. They're not asking for any sign. So 40 feet difference is the elevation right here when you subtract, and it's going to be basically 40 below point P. And now let's look at part 2, or question 2 of this applied project, which is really interesting actually. Basically it says the solution in part A might look smooth, but it might not feel smooth once you construct it, basically because the piecewise function defined, the piecewise defined function consisting of L1 of x, whatever, yeah, for L1 of x for x is less than 0, that's a straight line. F of x for this segment from 0 to 100, and L2 of x for greater than 100 here doesn't have a continuous second derivative. Yeah, so what this is saying, there's an abrupt change in the derivative of the functions, because you're going to go basically, yeah, as this graph shows, it's smooth here, then all of a sudden right here, you're going to go change to a completely new line that's only touching at one point. So to improve this, yeah, you decide basically to improve the design by using a quadratic function, the q equals ax squared plus bx plus c, only from 10 to 90 instead of 0 to 100, and connecting basically the linear functions on the outside by means of two cubic functions. So these ones with the missing parameters of k, l, m, and n, and p, q, r, s. These are basically from 0 to 10 and 90 to 100. And the reason for this is, if you were to look at it, so yeah, if you were to look at it graphically, so you have obviously the straight edge right here, the straight line across like this, but now you'll have a cubic function, and remember, cubics go up and down as opposed just to going curving up like parabola. So if we just look at the parabola first from, let's say, 10, that's this point right here, so this is the middle parabola, all the way to, yeah, all the way to 90. 90 should be somewhere here. So you're gonna have a parabola like this at this point, and then now we want to connect these instead of having a straight like at one point connection. So when we draw a cubic function, it would be something like this. It would be connected on more points, and then once it goes to here, it will start to curve down. So this is the cubic function, and also the exact same thing over here. So from 0, this 90, this is let's say 100 now. There's a second line across, let's say here. That's our L2. So there's our L2, our L1. I think this one's called Q. Yeah, this is called Q. Yeah, so yeah, that's Q, and G and H are the cubic functions. And then basically from here, from 90 to 100, do we want to, yeah, so this one is, yeah, this one is G, and now we want to connect from here to here with another cubic function. That's going to look something like this. And then as you can see, it's going to curve down, connecting more points, and it goes back up. This would be our H. So the idea is to basically have more points touching, or a smoother line, as opposed to one point in this simplified line and parabola. Now this question is actually going to be pretty complex, so I'll have to use a calculator for this, or a matrix calculator. Basically this states, write a system of equations in 11 unknowns, because remember there's 4 right here, 4, 8, and then the a, b, c, d, that's 11 unknowns that ensure the functions and their first two derivatives agree at the transition points. So we have 11 unknowns, and we can find actually 11 or 12 functions. I'll illustrate that in a bit. And it basically says solve the equations part A with the computer algebra system to find the formulas for Q, G, and H, and then plot these all together and compare with the problem in question 1. So now question 2A is basically finding the system of equations. So first let's make a table, so what the calculus book has. So you'll have a table. So I'll call this interval. So the first column is going to be an interval, and it's going to be from, let's say, negative infinity to 0, and these are open brackets, meaning at the points we're not going to be touching. So it's not defined at 0. So at this point here, we'll have a function. I'll write this down. I'm just trying to break down this, but in a table. So from infinity, negative infinity, all the way to 0, we're going to be having this function L1 of x, and this one's going to be equal to L1 of x equals to 0.8x. We've already defined this function, so 0.8 of x. I'll put this like this, and now, so that's the function f. And then now, if we want to find the first derivative, I'll make another. Let's make a column here. Let's go first derivative right here, and then this is gonna be 0.8. So L1 prime of x equals to 0.8. And then the second derivative on this column will have L1 double prime of x equals to 0 right here. So that is our function there. And then if we were to go with now from, actually now it's going to be from close bracket from 0, that's defined there, and then up to 10, we'll go open bracket not defined, so for the next function. So this one's going to be our cubic function, g of x equals to kx cubed plus lx squared plus mx and then plus n. If we take derivative of this one, we'll get g prime of x, And I'll show you why we do this, because we could use it to develop a system of equations. This would be 3kx squared plus lx, L2 of x right here, then plus m. And then the second derivative is just going to be g double prime of x equals 2, 6. I don't mind, it's going to be a bit, it's a bit messy here, but I'll fix this up in a bit. This is going to be 6kx plus 2l, etc. So that's the equation. And then we keep doing this further and further. Then the next one's going to be, well, 10 up to 90. That's our parabola. We'll call this q of x. That's our parabola. Then we go further. We'll get 90 open bracket up to 100. And this is going to be close bracket. And then after that, this is going to be our gh of x, our other cubic function. Then we get to 100 up to infinity. That is just our, this is just our straight edge right here, L2 of x. And here basically, just to make it neater, I put all in a table right here. So we'll have our 5 functions, L1, G, Q, H, and then L2 of x, and we take derivative, and then second derivative of each single one of them. And now the reason we do this one is, and now we apply, because we know that the conditions at each of these points, at this 0, at this 10, this 90, this 100, and this 100, basically have to have equal derivatives and second derivatives, etc. Yeah, because we want to match, in order to make it smooth, we need to make sure all the derivatives, first derivatives, and the functions all match at these points, or these 4 points, 0, 10, 90, and 100. And what I mean by that is we have to apply these 3 conditions at each point. The derivative, the function, and the derivative and second derivative have to all match up at each point of the 2 closest functions. So basically at x equals 0, g0 and L1 of 0 have to be equal. This is basically the cubic, it's the straight lines. If we were to do this one, we'll have, if you were to write this one out, remember g of 0 is just this function right here. And if we just look above here, plug in 0, we get n, and then equals to the right side, which is L1 of 0, plug that in, we'll get 0. So we get n is equal to 0. That's what we found out. Now the second part here, we go plug in 0, and here we get m equals 2. Now the right side of this one is 0.8. So we get m is equal to 0.8. So we've solved for these two, 0.8. And now we got the third equation. This one, the derivative, we plug in 0, we get 2l, and this is 0. So we get 2l equals 0. This is the same thing as writing l equals 0. So it's the same thing. And if we continue this for every other equation, we will develop a system of equations. Yeah, and here basically I have put these in a table. So there's that n equals 0, m equals 0.8, 2l. Then instead, I don't have the time to do all these ones, but then if you just do this exact same thing with all the other equations, you get this, and we have a bunch of unknowns, etc. So this is solves for question 2a. And now question 2b basically says solve those equations in part A with the computer algebra system. Define formulas for qx, g of x, and h of x. So basically define all those 11 unknowns. And now here I've actually written up basically this Excel sheet. I've put up all those variables a, b, c, k, l, m, n, o, p, q, r, s, etc. And then on the right side is the constant in a giant matrix. I'll do it basically. If you haven't done matrices, I'll do that in the future. I'll do videos on that. But if you have, this is just a good side note on matrices. Basically, this is a way of solving these equations, and the way I've written it here, if we look at the first equation, n equals 0, I put all these above here. So if we were to write all of them as a function of every one of these constants right here, so and this just means n equals to 0 right here. So at this point, yeah, this is just n equals to 0. That's the first equation. The second one is just m equals to 0, because there's a 1 here. If there's a 0, it just means it's going to be 0 in front of that number. And then this one is going to be, this is m equals 0.8, 0.8. So the right side is this equal sign. So this would be all equal signs on the right, equal, equal, etc. These are just a way of writing it. And then when you look at these part here, I have these negatives here. And the reason is because of this ABC. If we look at, let's say, one of these functions here, the 729,000p, then there's Q, there's R and S. Those are these those are these numbers right here, 72981,900. But then we shift basically everything here on the left side and then make it a constant on the right side, which is going to be 0. So we put these on the left side, so you'll have negative 8100, negative 90, and negative 1. Exactly, it states right here. So now when you have this one, I have the answers here solved there, but you could just basically copy this. Actually, I mean copy just the first 11 columns right here. So there's actually going to be this is a 12 by 12 matrix, and right here, actually let's count this one. I think there's 12. So yeah, this is a 12 by 12 matrix, and solve these by going to this bluebit.gr matrix calculator. I'll have the link also in the description below. Basically, you can click. If you show instructions if you could just copy an Excel inside it and just say it's separated by tabs. Except this is just matrix one. You will need to solve system of linear equations. Click that button. Go to here. Copy this. I'm just copying, pasting. Again, put it as tabs. Make it more digits 6. And now we'll go back to this. We need to copy the right side now. So for system of linear equations in this calculator, you gotta do it like that. Paste this here. And we just go solve ax equals b. So basically that matrix is a, and x are variable matrix, and we get this stuff right here. So these are the answers, and then this just means that we set up, basically make this matrix in terms of this 1 1 1 1 1 across, and this is just a equals to negative 0.0133. B equals 0.9333, etc. And we have our this last one, S equals negative 3.244. So we have all the variables based on these matrix calculator. Yeah, and here I've basically copied and pasted just a table I made with all of the constants right here that we're looking for, the unknowns, and then it's basically in the matrix that this is in right now. So you would plug this into whatever matrix calculator you have. Like the one I showed is pretty good. Yeah, basically you could just solve this matrix at this website, bluebit.gr/matrix calculator/linear equations, etc. ASPX, not sure what that is. But anyways, what you end up with is the answers will be right here. I have these put in. You can also put them in fractions right here, because these are rational numbers that keeps going on, and these are actually in fractions as well, so you could write them as fractions. And there's the equation for Q. This is the center parabola, then the cubic functions, etc. here, G and H of X, and we also have the linear functions, L1 and L2 that are above. And here basically I've graphed every single one of these, L1, G, Q, H, L2, and F of X is the original parabola we got from question 1. That's just a basic parabola and 2 lines. So now I made a table from negative 50 all the way to 150 and calculated these out based on those equations that what we derived. Basically, when you graph it out, it looks something like this, where this function right here, this is our Q, and as you can see, the parabola, I mean the cubic function goes down like this and goes up, and when you compare it to, this is our F. So initially it was a bit lower, now it's going to be a bit higher, and then it basically matches up with, it just basically at this point right here connects with this cubic and this straight line better. So as you can see, this is the L1, this is G, this cubic function is H, and there's our L2, I believe. Yeah, this is L2. You can see the legend here as well, and it goes up and down. That's our G, and this goes up like that. So basically, as you can see, it's a bit higher, and it is smoother here. And this is, well, anyways, that's all for today. Yeah, that's all for today, actually. Anyways, it's a pretty long video. Hopefully you learned from this, and I have I'll put the links for the notes of these notes right here, and also this Excel sheet, all in the Dropbox links below. So make sure to check that out. It's a pretty long video. I also have copied and pasted that final graph in this document as well, and you can download that. You can also check out this pretty good calculator right here. Well, anyways, it's a pretty long video. I just want to go through this. This is just a small little basically look into the world of roller coasters and design, and this, they actually do stuff like this. It's pretty intense, just because they want to make it the best they can, especially with the powerful computers. Now you could calculate giant matrices like the ones I just showed, like the 12 by 12 matrix right there. Anyway, that's all for today. Hopefully you learned, and stay tuned for another math easy solution.